pop it in the view. Okay. So if you remember, the first move was to get rid of whatever the C value is, right? And that happened already in this case, right? You remember the standard or the general form for a quadratic. They changed the settings on me. All right, so ax squared plus bx plus c is equal to 0. That's the general form. We're looking for that c value to be moved over before we start completing the square. Well, they already did that. All right, so that's nice. All right, what we want to do to make it consistent with the approach that we used last time is get rid of that a value. All right, so, but again, we get rid of it using appropriate algebraic techniques. You can't just make it disappear. That'd be nice. But it'll also violate every rule of mathematics in existence. Right? So what we can do is we can divide each term by that leading coefficient of 4. You could divide an equation by any non-zero value that you want numerically, as long as you do it to each term, right, on both sides. It might create a fraction, and that's okay. Right? We have calculators. I mean, it's not ideal that we have a fraction, but we learned how to handle fractions with radicals and things like that. But the calculator will help us out if we get in a jam. All right, so that's going to give us n squared plus 4n, leave a little space to complete the square, is equal to 65 over 4. All right, don't put it in decimal form. All right, so I'm not saying it's okay to not put it in decimal form. I'm giving you a directive. I'm saying don't put it in decimal form. All right, you'll get an answer that's not consistent with the way that these answers should be represented. All right, so now we'll get into the completing the square process, and we do that by taking our b value. So a little side work here. Take our b value, cut it in half, square it. 4 divided by 2 is 2, squared is 4. That number gets added to both sides of the equation. All right, on the left side we factor, on the right side we combine. All right, you could do that by hand if you want, but you could also do it using the calculator. All right, if you're doing it in the calculator, I recommend you use alpha y equals n over d. You type in your 65 over 4 plus 4. It'll give you the answer in simplified form, which is really nice. All right, no additional steps needed. Alpha y equals n over d, numerator over denominator. All right, so this side, without really any extra thought, simplifies to 81 over 4. The left-hand side, that's our perfect square trinomial. That was the whole point behind the side work. If we did that right, and we did, then we would now have a perfect square trinomial that could be written as a binomial squared. We would take the square root of the first and the last terms, and carry down the sign of the middle term. All right, yeah.
Wait, should the 4 be a 2?
It should, yeah. Thank you. Oops. Take the square root of both sides. The whole point in completing the square is to write it as a binomial squared, which allows you to take the square root of both sides of the equation. Because we are actively taking the square root, we're the ones deciding to do it. So square root, square root. The left side, that's fine. The power of 2 and the radical are going to cancel each other out, so n plus 2. But since we're actively taking the square root on the right side, we have to attach a plus or minus there. All right, so when you take the square root, and this is one thing that we reviewed last week, when you take the square root of a fraction, that's the same as taking the square root of the top and the square root of the bottom separately. All right, square root of 81 is 9, square root of 4 is 2, but we put on that plus or minus. Doesn't matter where you put the plus or minus. I like to put it out in front. You could attach it to the 9 if you want. I probably wouldn't attach it to the 2, but you technically could do that also. But I put it out in front because in the next step, I'm going to subtract off the 2. And we'll get n is equal to negative 2 plus or minus. Now it becomes an operation. Negative 2 plus or minus 9 over 2. Now, because this is rational, right, not irrational, but rational, no radicals involved, I can't just leave it like this. So I split it and make two equations out of it. So I'd have n is equal to negative 2 minus 9 over 2, and n is equal to negative 2 plus 9 over 2. All right. So you could probably do this in your head if you wanted to. 9 over 2 is 4.5. Combine, go that route. Or you could do it this way. Negative 2 minus alpha y equals n over d, 9 over 2. The only thing with the TI you got to be careful about is when to use a negative sign and when to use a minus sign. We only use the minus sign when it's an operation, when you're subtracting one thing from another. If it's just a signed number, right? So like the negative 2 gets a negative. You wouldn't use a minus symbol there. All right. So that would be one result. Now, instead of typing this in all over again, I could just hit the up arrow a couple times, hit enter. It'll copy paste automatically my previous computation. Just go back and change that minus sign to a plus sign. You could also hit second enter or do the same thing. But I have my two answers now. N is equal to negative 13 halves. N is equal to 5 halves. All right, so it crunches the numbers for you. I mean, which is what you would expect a calculator to do. All right, so let's just do one more together. Trying to decide. Let's do number 5. 4 and 6 I'll do with period 2, and I'll get that video up on YouTube. All right. So again, whatever the a value is, we don't want that there. All right. So we're going to divide that out immediately. There's other ways to do this, but this is a pretty efficient way of going about it. You divide every single term, even if it creates a fraction. In this case, it works out beautifully. All right? It doesn't create a fraction at all. Every single term is even. So x squared plus 6x plus 16 is equal to 0. This is different from the concept of GCF. With GCF, I was saying you divide each term by the number, and then you don't just throw away the number. Here, you can kind of throw away the number because you're dividing both sides of an equation by that number, not just one side. All right. So we're not factoring. We're actually straight up dividing both sides of the equation. All right. Then I get rid of the c value using a valid algebraic technique, subtraction, property of equality. So I'd have x squared plus 6x, leave a little space to complete the square, is equal to a negative 16. All right. For my side work, I take the b value, cut it in half, square it. You get a 9, so I add that to both sides. On the left-hand side, I would factor x plus 3 squared, because again, the square root of the first term, the square root of the last term, carry down the sign of the middle term. But then on the right-hand side, I get something interesting. I get a negative 7. All right. So it's in this step And actually, when you do this enough, you'll start to realize that you could kind of call it quits a little earlier, but it's in the square root step where you realize, oh, wait a minute, I'm getting a square root of a negative number. Now that gives you an imaginary result. I would take you through, because you could actually come up with the imaginary answer using a letter I, but I don't want to confuse people, and I don't want you to get in the habit of doing something that the Regents isn't expecting you to do until it's time for you to get in the habit to do that thing. All right. So this is going to be imaginary. So we would say no real roots. All right. Emphasis on the word real, although you don't actually need to emphasize it. I'm emphasizing it. There are no real roots. We say roots, x-intercepts, solutions, blah, 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 whatever. I'm not saying there aren't any. I'm just saying the ones that exist are just not real. They're imaginary. They're different types of numbers. They're part of a different number system. All right? So there are roots. They're just not in the real number system. All right? So when you get to Algebra 2 and you talk about the complex number system, then you'll start to understand where those numbers went, where those roots went, why they exist the way they do. All right? So, but we have an example with rational numbers. We have an example with imaginary numbers. You could have a solution that involves irrational numbers. That would just have a radical in your answer. All right? So let's say you go back to the first one. If you got to this step here, and let's say, oh, actually, maybe even prior to that. No, I mean, I guess this is fine. You got to this step here, and maybe this is like a radical 7, for example. At that point, you would just stop, right? Because you wouldn't be able to go any further, all right? So that's just something to keep in mind. If you have a radical, you don't have to break up the plus or minus. But if you don't have a radical, you do. All right. So what I'd like you to do with the remaining time is tackle, let's see, page 35, and take a picture submitted on Schoology by midnight, please. The only difference between these problems and the ones we were doing last week in terms of solving by completing the square is that they have a leading coefficient. All right, that leading coefficient is other than 1. All right, so here I have a leading coefficient of 5 versus, like I was saying, leading coefficient of 1. All right, we still need to have it in the appropriate form where the C value is the only thing on the right-hand side. All right, so we can make that adjustment first. We could do it after the fact. It really doesn't make a difference. I'll do that first. All right, so I'm going to add a, ooh, that's a little thick. I'm going to add a 21 to both sides. That's going to give me a 5y squared is equal to 10y plus 21. I'm going to subtract the 10y from both sides. Feel free to do this in your head or do it all in one step. It's up to you. All right, I'm just doing it for note-taking purposes. I'm just being a little bit more explicit. All right, so we have 5y squared minus 10y. I would leave a little blank to complete the square is equal to 21 because this canceled out. All right, now there is a formula that allows you to complete the square all in one shot, even with a leading coefficient other than 1. We're just not going to use that formula because it's another formula. All right, we already have a formula, so let's just stick with what we know for now. All right, so to make this work with the formula that we know, we need to divide each term by whatever the a value is. All right, you could divide or multiply an equation by whatever non-zero term you want, as long as you do it to every term within the equation. All right, so I'm just choosing to divide everything by a 5 here. Still an equivalent equation, still has the same value, just has a different appearance. All right, so I'm looking at y squared minus 2y is equal to, with that little gap there, 21 over 5. I mean, it would be nice if that was 20 over 5 and gave me a clean 4, but it didn't, so here we are. So I'm just going to leave it as 21 over 5 because I can't reduce it. We do not want to turn it into a decimal. All right, you're just going to make things more challenging for yourself if you convert to decimal form. So don't do that. So it's not like suggesting that you keep it in fraction form. I'm saying you must keep it in fraction form. All right. So now we have something similar to what we started with last week. So you have to do that little extra work to get yourself in the right format. But now I can do my little side work, you know, that little area that I created, the side work. All right, I take my b value, divide it by 2, and square it. So in this case, my b value is a -2, divide it by 2, and square it. Well, -2 divided by 2 is a -1. -1 squared is a +1. All right, any number squared is going to be positive. That's the number that I add to both sides. So I'm going to add a 1 to both sides of the equation. I'll do that in different color. All right. Now, I can get a common denominator and add these two numbers together on the right-hand side. I don't want to. I'd rather just let the calculator do it. Take a little break from thinking here. So alpha y equals n over d. It's a good feature on the calculator. If I put in the 21 over 5, and then add to that 1, it's not only going to add the two values, but it's going to put it in simplest fraction form for me, which is great. All right, so the left-hand side I'll still have to deal with, but the right-hand side I now know is the square root. Oh, well, it's not square root yet. It will be in a minute. 26 over 5. All right. The left-hand side is now a perfect square trinomial. That's the whole point behind that b over 2 squared business. All right. So now that it's a perfect square trinomial, we could use the shortcut for putting it into its factored form. The square root of the first term goes here. The square root of the last term goes here. And the middle sign, the term of the sign of the middle term, goes in the middle of your binomial. All right, so I have a y, I have a 1, and a minus sign. All right. So now I'm going to take the square root of both sides. All right. Square root of both sides gets rid of the radical on the left. I'm sorry, it gets rid of the power of 2 on the left, but it introduces a radical on the right. All right, so I'm looking at, I'll just continue on over here. Y minus 1 is equal to plus or minus the square root of 26 over 5. All right. Now, depending on how your answer has to be represented, that it might be okay, but we might have to simplify. All right. So assuming that we could represent our radical in any form, this would be okay. The square root of a fraction, that's fine. Right? But maybe you need to rationalize the numerator. Maybe you need to rationalize the denominator. All right. So we don't know what the expectations are for this question because they weren't given to us. The beauty of it is if the expectations aren't given to you, there are no expectations. So you can put it in any way that's conceptually simple, right? And so this is one of those ways. So I'll add a 1 to both sides. I'm going to move things over just a smidge. And I would get y is equal to 1 plus or minus the square root of 26 over 5. All right, it's not a pretty answer, but it's a correct answer. All right. Now, if I did need to rationalize, so let me just show you because I know it's like a tedious extra step, but you could be expected to do it in some circumstances. I mean, I'll just be upfront about it. I'm definitely gonna expect you to do it. It's just a question of whether the Regents is going to expect you to do it. So if you needed to rationalize, I would have to take this fraction, split it up, I need to get the radical out of the bottom, all right? So the technique that we learned for rationalizing is you multiply top and bottom of the fraction by the thing that you want to get rid of, the radical that you want to get rid of. So the radical I want to get rid of is the radical over the 5, so radical 5 gets multiplied top and bottom. So on the bottom I have a nice clean 5. On the top I have the product of 26 and 5, which would be 130. If I just did the mental math correctly, hopefully. So then I would bring down the 1 plus or minus, and I would have y equals that. So it could be either or. It could be this answer, or it could be that answer. Both of them are correct. Both of them are simple. Right? The fraction is in simplest form, that 26 over 5 under the radical. It's just a question of how the directions indicate that your radical needs to be represented. Right? But you'll notice in none of these instances did I give you a decimal answer. All right? Whether it's the unrationalized form or the rationalized form, each case was a fraction, not a decimal. All right, so this answer or this answer. All right, so that was a pretty crunchy one, but let's do something a little less so. All right, so in number 6, like I said, you could move the C value over first, or you could divide first. This time I'm going to divide first. I'm going to divide out the 7. Always whatever the A value is. The leading coefficient. Divide each term by that. So we're looking at b squared minus 2b minus 8 is equal to 0. All right, I need to get rid of the c value. So I'll do that by adding it to both sides. B squared minus 2b, leave a blank to complete the square, is going to be equal to 8. So then I do my b over 2 squared business, my side work. You know, you don't have to write side work. I just write it for your benefit. Just somewhere you're doing that side work, unless you're doing it in your head. If you're doing it in your head, then there's no need to write side work or anything like that. But I got my negative 2. I'm cutting it in half. That's not a 2. Cutting it in half and squaring it. Negative 2 divided by 2 is negative 1 squared. Negative 1 squared is a positive 1. So that's the number I'm adding to both sides. So you can see the right-hand side here is much simpler. It's just a nice clean 9. And that's the difference between this question and the previous one. You know, in terms of difficulty, it all depends on what your C value is. Right? If your C value works out to be perfect once you complete the square, then it's going to be a pretty easy computation. If it doesn't, then you could end up with a question like I think it was number 4. Right? So left-hand side is going to be a binomial squared. So whatever the square root is of your trinomial, the leading term and the constant term, b and 1, that goes right into the binomial. You just bring along for the ride the sign of the middle term. All right. Then you go ahead and take the square root of both sides. All right. The radical and the power of 2 will cancel each other, leaving you with just a b minus 1. On the right-hand side, again, because we are deciding, we are the ones taking the square root. It wasn't presented to us as a radical. We initiated the square root process. We have to include a plus or minus. Now this one's rational, so much easier. Add a 1 to both sides. we always put the plus or minus term after whatever number we're adding to the both sides of the equation. So 1 plus or minus 3. The one thing about a rational case is that you do have to split up the equation and make two separate equations. All right, so we're looking at b is equal to 1 minus 3. B is equal to 1 plus 3. So there's little trade-offs where you have like, all right, so there's a radical in there, so you don't have to do this last step here. But if there is no radical, you do. But if there is a radical, you have to do work in other ways, you know? So it all kind of balances out in the end. It just feels like there's always another step. You know, when you start getting more and more experience with this, it'll be frustrating because it'll be like, oh, but did you consider this? Did you do that? And you're like, oh, I forgot. It'll feel like you're forgetting one step in every problem until you've experienced a wide variety of different situations, and then you kind of nail down the different variations of it, and it gets a lot easier from there. All right, so I'll leave this up on the big board, but what I'd like you to do is page 35. All right, that's your assignment. So you'll complete that and take a picture of it and pop it up on Schoology by midnight.